Something out there is changing course, and its target could be us. Interstellar visitor 3I Atlas, once thought to be just another frozen wanderer, has begun to accelerate, subtly, steadily, in a direction that shouldn't even be possible. According to a series of independent analyses based on Avi Loeb's report of a non-gravitational acceleration near perihelion, if it keeps pushing for just 50 days, it could shift its velocity by 86 meters per second, enough to line up with Earth on December 19th, 2025. Is it physics or propulsion? A coincidence of dust and sunlight, or a deliberate maneuver? And right alongside this motion, there's a frequency. 1.4 gigahertz. Faint pulses, rhythmic, almost mathematical, echoing through the void, almost like a reply. Could this be coordination? Stay with me, because by the end of this video, you'll understand why some of the world's sharpest scientists are whispering the unthinkable. 3I Atlas isn't just passing by, it may be maneuvering toward us. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Breaking claim. Something is coming. Right now, somewhere between Mars and Jupiter, a visitor from another star system is moving through our solar system. This isn't speculation. This isn't science fiction. The object exists. It has a designation. 3I Atlas. It was discovered on July 1st, 2025 by the Asteroid Terrestrial Impact Last Alert System in Chile. What makes this object extraordinary isn't just that it came from another star. What makes it extraordinary is what it might be doing right now. A series of posts appeared on X, the social media platform formerly known as Twitter. An independent researcher laid out a calculation that stopped people in their tracks. The claim goes like this. If 3I Atlas sustained a non-gravitational acceleration of approximately 0.02 millimeters per second squared for roughly 50 days, it could achieve a velocity change of about 86 meters per second. That velocity change, according to the claim, could allow the object to line up with Earth around December 19th, 2025. Let me say that again. Line up with Earth. The post went further. They suggested this wasn't random. They framed it as intentional maneuvering. They even mentioned 1.4 gigahertz pings, alleged communications, possible course corrections, handshakes between an alien probe and something near Mars. Now, before you close this video thinking it's just another conspiracy theory, consider what we actually know. The object is real. The trajectory is hyperbolic, meaning it's not bound to our sun. It came from interstellar space. Its perihelion, the closest point to the sun, occurred around October 30th, 2025. And yes, there are reports of non-gravitational acceleration. That means the object is moving in ways that gravity alone cannot explain. Non-gravitational acceleration is not magic. It's physics we don't fully understand yet in this context. When an object in space deviates from the path that gravity predicts, something else is pushing it. Usually that something is outgassing. Comets do this all the time. Ice turns to vapor, jets of gas shoot out, and the object gets a tiny push. 0.02 millimeters per second squared doesn't sound like much. It's about 1/50,000th of Earth's gravity. But in the vacuum of space, over days and weeks, tiny pushes add up. Here's where it gets interesting. This is only the third confirmed interstellar object we've ever detected. The first was Oumuamua in 2017, the cigar-shaped mystery that sparked endless debate. The second was Borisov in 2019, which looked like a normal comet. Now we have 3I Atlas. And unlike the others, this one is showing behaviour that makes people ask uncomfortable questions. What are the stakes here? If this is just a comet, albeit an unusual one, it's still scientifically valuable, a piece of another star system, passing through ours, offering clues about planetary formation elsewhere in the galaxy. But if the acceleration is intentional, if something is steering this object, then we're looking at a different category of event entirely. We're looking at the possibility, however remote, of an engineered object from another civilization. The objective of this investigation is simple. We're going to examine the claim. We're going to look at the data, the assumptions, the arithmetic, and the speculative leaps. We're going to explore what we know versus what we're guessing, and we're going to look ahead to what's coming in late 2025 and early 2026, when observations could confirm or destroy this hypothesis entirely. This isn't about feeding paranoia. It's about understanding what's real, what's possible, and what's just noise. The truth is, space is full of things we don't understand yet. Every now and then, something comes along that challenges our models. 3I Atlas might be one of those things, or it might be a perfectly normal interstellar comet that happens to be outgassing in ways that look strange to us. By the end of this film, you'll be asking yourself a question. Natural comet, alien probe, or something in between. You'll have the tools to form your own judgment. You'll understand the science, the math, the observational campaigns, and the broader implications, and you'll know what to watch for in the coming months. The structure of this investigation unfolds in 3 acts. Act 1 will present the claim and the data. We'll look at what 3I Atlas actually is, what the numbers show, and what assumptions underlie the Earth intercept scenario. Act 2 will dive into the deeper speculations, the controversies, the natural versus exotic explanations, and the social media narratives that have amplified this story. Act 3 will widen the scope to recent breakthroughs in space science, artificial intelligence, and radio astronomy, connecting 3I Atlas to the cutting edge of discovery. Then we'll wrap up with what's next and what you should be watching for. One more thing before we move forward. The universe is indifferent to our comfort. It doesn't care whether we're ready for what it reveals. For most of human history, we believed we were alone, that Earth was the center of everything, that the cosmos revolved around us. Every major discovery since then has been a step toward humility. We learned Earth orbits the Sun. We learned the Sun is one of billions. We learned galaxies stretch beyond counting. Now we're learning that objects from other star systems can visit us. What happens when one of those visitors does something we can't easily explain? Next, we look at what the data actually show, so you can judge for yourself whether this claim holds water or evaporates under scrutiny. Part 2. What the data actually show. The discovery of 3I Atlas happened on July 1st, 2025. The Asteroid Terrestrial Impact Last Alert System, a network of telescopes in Chile designed to spot near-Earth objects, picked up something unusual. At first, it looked like any other faint dot moving across the sky, but orbital calculations quickly revealed something extraordinary. The trajectory was hyperbolic. A hyperbolic trajectory means the object is not bound to the Sun. It's moving too fast to be captured by solar gravity. It came from somewhere else, passed through our solar system, and will leave again, heading back into the void between stars. This is the hallmark of an interstellar visitor, the designation 3 I was assigned, the third interstellar object ever confirmed. Let's talk about the orbit. Perihelion, the closest approach to the Sun, occurred around October 30th, 2025. The distance was approximately 1.36 to 1.4 astronomical units. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So perihelion put 3I Atlas somewhere between 203 and 210 million kilometers from the Sun, roughly inside the orbit of Mars. The closest approach to Earth is predicted for December 19th, 2025. The distance will be about 1.8 astronomical units, roughly 268 to 270 million kilometers. To put that in perspective, the Moon is about 384,000 kilometers from Earth. This object will pass at a distance equivalent to about 700 times the Earth-Moon distance. Far, very far, outside any conventional definition of a close call. Now we get to the anomaly. In a post on Medium, Avi Loeb, the controversial Harvard astrophysicist known for his work on Oumuamua and the search for extraterrestrial technology, reported something unusual. Astrometry data from the Jet Propulsion Laboratory and the Atacama Large Millimeter Array showed a deviation from the expected path. The object was not where it should be if gravity alone was guiding it. The offset was about 4 arc seconds, a tiny angular shift, but significant when you're tracking something across millions of kilometers. Loeb calculated a non-gravitational acceleration of approximately 0.02 millimeters per second squared. He then applied a momentum conservation equation to explore what could cause that. If outgassing is the driver, meaning jets of vapor pushing the object, then the rate of mass loss must be substantial. His calculation suggested that at least 1/6 of the object's mass would need to evaporate over the course of about a month to produce that level of acceleration. Let's pause on that. Non-gravitational acceleration is not exotic by itself. Comets experience it routinely. When ice sublimates, turning from solid to gas, it escapes from the surface and creates thrust. It's a rocket effect, weak but measurable. The challenge, with 3i Atlas, is the scale. If the object is as massive as some estimates suggest, tens of billions of tons, then losing 1/6 of that mass in a month should produce a spectacular cloud of gas and dust, a visible coma, a tail, something we could detect. Visually, 3i Atlas has shown some unusual features. Images reveal a jet structure, possibly directed toward the sun rather than away, which is uncommon. The colour of the object has also drawn attention. Reports describe it as bluer than the sun, potentially indicating ionised carbon monoxide rather than typical dust. These are clues, but they're not conclusive. Comets can be weird. Interstellar comets, even more so. What does the data not show? Loeb himself does not claim the object is on an Earth intercept trajectory. He does not say it is intentionally manoeuvring toward us. The data show an acceleration. They show an offset. They suggest something interesting is happening. The leap to Earth intercept to intentional steering comes from elsewhere. It comes from the social media post that took Loeb's numbers and ran a calculation. Here's the key distinction. The data are intriguing but not inexplicable. A hyperbolic interstellar object with some outgassing and a jet structure? That fits within known physics. It's on the unusual end, sure, but not impossible. The question is whether the data support the bold claim that 3i Atlas is actively altering its course toward Earth, or whether someone has taken real data and added layers of assumption to reach a dramatic conclusion. So far, what we have is this: an interstellar object, real and confirmed, a trajectory that brings it relatively close to Earth but still very far away, a non-gravitational acceleration that could be outgassing or could be something else, and a calculation that shows mathematically how a small continuous push over 50 days could result in a significant velocity change. Is that enough to claim the object is lining up with Earth? That's the question we'll tackle next by examining the math and the assumptions that turn data into narrative. Part 3. Extrapolation to Earth intercept. Maths and assumptions. Let's do the arithmetic. The social media claim starts with a simple equation from classical physics. Acceleration times time equals velocity change. If you have a constant acceleration of 0.02 millimeters per second squared and you sustain it for 50 days, what velocity change do you get? 50 days is 4,320,000 seconds. Multiply that by 0.02 millimeters per second squared, which is 2 times 10 to the negative 5 meters per second squared, and you get approximately 86.4 meters per second. That's the delta V, the change in velocity. The math is correct. There's no dispute about the arithmetic itself. Now let's talk about displacement. If you apply a constant acceleration, over time you don't just change velocity, you also change position. The displacement under constant acceleration is 1/2 times acceleration times time squared. Plug in the numbers. 1/2 times 2 times 10 to the negative 5 meters per second squared times 4.32 times 10 to the 6 seconds squared. You get approximately 1.87 times 10 to the 8th meters. That's 187,000 kilometers, roughly half the distance from Earth to the Moon. So yes, the numbers are non-trivial. A small but continuous thrust over 50 days could shift an object's path by hundreds of thousands of kilometers. In the context of orbital mechanics, that's significant. It could change where and when an object crosses a particular plane. It could alter a missed distance. It could theoretically convert a distant flyby into a closer one. But here's where assumptions start to pile up. The calculation assumes the acceleration continues unabated for 50 days. Does it? We don't know. The acceleration was measured at a specific point, near perihelion. Whether it persists for weeks or months is unclear. Outgassing typically varies with distance from the Sun. As an object moves away from perihelion, solar heating decreases, and so does the rate of sublimation. The thrust might weaken or stop altogether. The calculation also assumes the acceleration is applied in exactly the right vector. Direction matters as much as magnitude. If the thrust is sideways relative to Earth's orbit, it might change the orbital plane but not significantly alter the missed distance. If it's prograde, speeding the object up, it changes arrival time. If it's retrograde, slowing it down, same thing. If it's radial, pushing toward or away from the Sun, it changes the semi-major axis and eccentricity. Without knowing the direction of the acceleration, integrating the velocity change into a trajectory prediction is speculative. Timing is another critical assumption. The object has to apply the thrust at the right time and in the right direction, such that the resulting path intersects Earth's orbit when Earth is actually there. Earth moves at about 30 kilometers per second around the Sun. It covers vast distances in days. Hitting a moving target requires precise timing and vectoring. A shift of 187,000 kilometers might move the crossing point, but if Earth isn't there at that moment, the intercept doesn't happen. Then there's the question of energetics and mass. If the object is as massive as estimates suggest, tens of billions of tons, sustaining a thrust requires enormous energy. If it's natural outgassing, the mass loss rate must be high, as Loeb calculated. If it's artificial, it implies a propulsion system capable of long-duration thrust. Either scenario strains plausibility unless we see supporting evidence. Finally, there's the issue of perturbations. Space is not empty. Solar radiation pressure, the gravitational pull of planets, solar wind, even the Yarkovsky effect can all influence a small body's trajectory. The simple calculation assumes these are negligible or average out, but in reality they add noise and uncertainty. A purely deterministic 50-day burn is an idealization. Let me use an analogy. Imagine you're driving on a highway. You know you can accelerate 60 kilometers per hour faster than your current speed. That's like knowing your delta V. But merging into the right lane at the right time to reach a specific exit requires more than just speed. You need to know where the exit is, how fast traffic is moving, when to accelerate, and in which direction to steer. The arithmetic of velocity change is one thing, the geometry and timing of orbital mechanics is another. The social media extrapolation assumes the acceleration was acting in a useful direction for Earth lineup. We don't have evidence for that. The data show some acceleration, but not its vector relative to Earth's orbit. The claim adds, this acceleration is purposeful and Earth targeting. That's an interpretation layered on top of the data, not derived from it. Here's what we know versus what is assumed. We know there's a non-gravitational acceleration. We know it's small but measurable. We know the object's orbit brings it relatively close to Earth in December. We assume the acceleration persists for 50 days. We assume it's pointed in the right direction. We assume the timing aligns. We assume no other factors interfere. And we interpret all of that as intentional maneuvering toward Earth. Each assumption is a link in a chain. Break one link, and the whole claim collapses. The question isn't whether the math is correct. It is. The question is whether the real world conforms to the assumptions. Next, we'll look at the actual trajectory and miss distance to see whether a shift of 86 meters per second could realistically convert a 270 million kilometer flyby into something more ominous. Part 4. Object's trajectory and miss distance reality. The official numbers are clear. According to NASA and the European Space Agency, 3I Atlas will pass Earth at a distance of approximately 1.8 astronomical units on December 19, 2025. That's about 268 to 270 million kilometers. To give you a sense of scale, 1 astronomical unit is the average distance from Earth to the Sun, roughly 150 million kilometers. So 1.8 astronomical units means the object will be nearly double the Earth-Sun distance at its closest approach. This is not close. Not by any standard used in planetary defense. An object is considered potentially hazardous if its orbit brings it within 0.05 astronomical units of Earth, about 7.5 million kilometers. 3I Atlas will pass at more than 30 times that threshold. NASA and ESA have both stated explicitly that the object poses no threat to Earth. So how do miss distances work in orbital mechanics? When an object approaches on a hyperbolic trajectory, its path is determined by its velocity, direction, and the gravitational influences it experiences. The miss distance is essentially the closest point of approach, calculated from the object's trajectory relative to Earth's position at a given time. For 3I Atlas, that calculation yields 1.8 astronomical units on December 19th. Now let's address the central question. Could a velocity change of 86 meters per second significantly alter that miss distance? The answer is yes and no, depending on context. Yes, in principle, A delta V of 86 meters per second applied over 50 days could shift the object's trajectory by hundreds of thousands of kilometers. As we calculated earlier, the displacement could be around 187,000 kilometers. That's not nothing. In orbital mechanics, small changes in velocity can produce large changes in position over time, especially if applied early in the trajectory. But no, converting a 270 million kilometer miss into an Earth impact would require far more than 86 meters per second, unless the vector and timing were extraordinarily favorable. The object is moving at roughly 60 kilometers per second, 60,000 meters per second. 86 meters per second is less than 0.15% of its total velocity. To change the trajectory enough to shift the miss distance from 270 million kilometers to zero, you'd need either a much larger delta V or an almost perfect alignment of thrust direction and timing. The direction of the thrust is everything. Imagine the object's trajectory as a line through space. If you push sideways, perpendicular to the velocity vector, you change the orbital plane. You might shift the path by 100,000 kilometers laterally, but that doesn't necessarily bring it closer to Earth. If you push forward or backward along the velocity vector, you change the arrival time. The object might reach the Earth-Sun plane earlier or later, but again, that doesn't guarantee a closer approach unless Earth happens to be in that exact spot. If you push radially toward or away from the Sun, you alter the shape of the orbit, the eccentricity, and the perihelion distance. There's a concept in orbital mechanics called the B-plane. It's a virtual plane perpendicular to the incoming trajectory, used to calculate where an object will cross relative to a target. Think of it like a dartboard. The bullseye is Earth. The object's trajectory pierces the plane at some point, and the distance from the bullseye to that point is the miss distance. A small velocity change can shift where on the plane the object crosses, but moving from the outer edge of the dartboard to the centre requires a very specific push. Without knowing the direction of 3I Atlas's non-gravitational acceleration relative to Earth's position, we can't say how much the missus distance would actually change. The social media claim assumes the push is in the right direction. That's a big assumption. There's also the matter of the object's mass. Estimates suggest 3I Atlas is massive, potentially more than 33 billion tons, with a diameter of several kilometres. Manoeuvring a body of that size is difficult if the mechanism is natural outgassing. You're essentially trying to steer a mountain by evaporating ice off its surface. If the mechanism is artificial, it implies an engine or propulsion system of tremendous power. Either way, the physics is challenging. NASA and ESA scientists who have access to the full astrometric data and orbital models have concluded the object is not on an Earth intercept course. They factor in uncertainties, perturbations, and potential non-gravitational forces. Their models show a safe passage. If the numbers suggested otherwise, if there were even a small chance of impact, the alarm bells would be ringing. Planetary defense networks exist precisely to identify and track potentially hazardous objects. 3I Atlas is not on their threat list. So the miss-distance reality check comes down to this. The geometry and timing make an Earth impact scenario very unlikely at this stage. The object would need a much larger velocity change, applied in a very specific direction, at a very specific time, to convert a 270 million kilometre flyby into something dangerous. The numbers might look alarming if you focus only on the arithmetic of delta V, but the full picture, the orbital mechanics, the timing, the miss distance, all point to a distant passage. That doesn't mean the object is uninteresting. Far from it. The non-gravitational acceleration, the unusual features, the sheer fact that it's an interstellar visitor, all make it scientifically valuable. But the Earth intercept scenario, the claim that it's lining up with us, that remains speculative. Next, we'll explore the observational campaign ramping up right now, the telescopes pointing at 3I Atlas, and the testable predictions that will soon reveal whether this object is a comet, a probe, or something in between. Part 5. Observational Campaign and Testable Predictions. The next few months are critical. Between now and early 2026, 3I Atlas will be under intense scrutiny. Telescopes around the world and in space are already tracking it. The perihelion passage occurred around October 30th, 2025, when the object was closest to the Sun. Now it's heading outbound, moving toward its December 19th close approach to Earth. This is the observation window and it won't last forever. Once the object moves past Earth and heads deeper into the outer solar system, it will fade from view. The major instruments involved in this campaign include some of the most powerful tools humanity has built. The Hubble Space Telescope can capture high-resolution images in visible and ultraviolet wavelengths. The James Webb Space Telescope, with its infrared capabilities, can detect heat signatures and analyze the composition of any gas or dust surrounding the object. Ground-based observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii are also contributing. Radio telescopes are listening for any unusual emissions, and closer to home, Mars orbiters might catch a glimpse as 3I Atlas passes relatively close to the red planet. There's also an interesting coincidence. On November 4th, 2025, the European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, will pass within approximately 64 million kilometres of 3I Atlas. That's not close enough for a dedicated flyby, but JUICE's instruments might be able to gather data from that distance. Every bit of information helps. Avi Loeb and other researchers have laid out testable predictions. These predictions hinge on whether the non-gravitational acceleration is due to natural outgassing or something else. If outgassing is the cause, the mass loss should be substantial. Loeb's calculation suggested at least 1/6 of the object's mass evaporating over roughly a month. That should produce a massive cloud of gas and dust, a visible coma, probably a tail stretching behind the object as solar wind pushes the particles away. So the first prediction is straightforward. If the acceleration is natural, telescopes should detect a large gas and dust envelope. Spectroscopy should reveal the presence of volatiles like water, carbon monoxide, carbon dioxide, or methane. The object should behave like a comet, showing all the classic signs of sublimation-driven activity. But if no large cloud appears, if the mass loss is minimal or absent, then the natural outgassing hypothesis weakens. That would be a significant result. It would mean the acceleration is coming from something else, something that doesn't require ejecting large amounts of material. That's when non-natural or technological explanations start to look more plausible. The measurements to watch include astrometric residuals, the differences between where the object actually is versus where a purely gravitational model predicts it should be. These residuals reveal the magnitude and direction of any non-gravitational forces. Over the coming weeks, as more observations accumulate, astronomers will refine the orbit and quantify the acceleration with greater precision. Spectroscopy is another key tool. By splitting the light from the object into its component wavelengths, scientists can identify the molecules and atoms present. 3I Atlas has already been noted for its unusual colour, described as bluer than the Sun. That could indicate ionized carbon monoxide, a signature of certain types of comets. Or it could mean something else. Detailed spectroscopy will tell us more about the composition and whether it matches known cometary chemistry. Imaging is important too. The morphology of any coma or tail, the structure of jets, the presence of asymmetries, all provide clues. Some reports mention an anti-tail, a jet directed toward the Sun rather than away from it. That's unusual but not unheard of. Comets occasionally show forward-directed features due to geometry or rotation. High-resolution images will clarify whether what we're seeing is consistent with natural processes. Then there's radio astronomy. The social media posts claim the object was sending 1.4 GHz pings, alleged communications or course correction signals. That's entirely unverified, but radio telescopes will be listening anyway. If there are any unusual emissions, whether at 1.4 GHz or any other frequency, they'll be detected and analysed. Radio signals from a comet are rare but possible, usually associated with plasma interactions. A strong structured signal would be another matter entirely. There are challenges to this observational campaign. Timing and geometry matter. Around perihelion, the object was close to the Sun in the sky, making it difficult to observe without being blinded by solar glare. Now, as it moves away from the Sun and toward Earth, visibility improves. But by late December, after the close approach, it will start fading as it moves farther from both the Sun and Earth. The window is narrow. Weather, telescope availability, funding, and coordination all play roles. Not every telescope can observe every night. Data need to be reduced, analysed, peer-reviewed, and published. Science moves slower than social media. The claims might spread in hours, but the observations take weeks or months to confirm or refute. Still, this is an exciting time. We're watching a visitor from another star system in real time. The same telescopes that peer at distant exoplanets, that probe the chemistry of alien atmospheres are now turned towards something passing through our own neighbourhood. It's a rare convergence of opportunity and technology. By early 2026, we should have answers. If 3I Atlas behaves like a comet showing massive outgassing, a coma, a tail and spectroscopic signatures of volatiles, then the natural explanation holds. The non-gravitational acceleration was just a comet doing comet things, perhaps more dramatically than usual because of its interstellar origin and composition. But if the observations come back showing minimal mass loss, no significant cloud, and yet the acceleration persists or shows directionality inconsistent with jetting, then we have a problem. Not a disaster, but a scientific puzzle that doesn't fit neatly into our models. That's when the conversation shifts. That's when the exotic hypotheses, the ones we'll explore next, stop being idle speculation and start demanding serious consideration. The next act of this investigation dives into the natural versus non-natural debate, the role of social media in amplifying claims, and what it would mean if 3I Atlas turned out to be something other than a comet. Part 6. Non-gravitational acceleration, natural explanations. Comets are dirty snowballs, or at least that's the simplification we teach in introductory astronomy. A comet nucleus is a mixture of ice, rock, and organic compounds. When it gets close to the sun, solar radiation heats the surface, causing ices to sublimate, turning directly from solid to gas without passing through a liquid phase. The escaping gas carries dust particles with it, forming a cloud called a coma and often a tail that streams away from the sun. This outgassing doesn't just create a visual spectacle, it also creates thrust. The gas molecules carry momentum. As they leave the nucleus, they push back on the comet itself like a leaky balloon zipping around a room. The effect is small, but measurable. It's called a non-gravitational force, and astronomers have been detecting and modelling it for decades. So when Avi Loeb reports a non-gravitational acceleration of 0.02 millimeters per second, squared for 3I Atlas, the first assumption is that it's outgassing. That's the default hypothesis, the most natural explanation. But the details matter. Loeb applied a momentum conservation equation to estimate how much mass loss would be required to produce that acceleration. The formula is straightforward. The force on the comet is equal to the rate of mass loss times the velocity of the outflowing gas. Force equals mass times acceleration, so you can rearrange to find the mass loss rate. If the outflow velocity is a few hundred meters per second, typical for cometary jets, and the acceleration is 0.02 millimeters per second squared, you can solve for how fast the comet is losing mass. The result is striking. If 3I Atlas has a mass of around 30 billion tons, the calculation suggests it would need to lose roughly 5 billion tons per month to sustain that acceleration. That's about 1/6 of its total mass in 30 days. Over a few months, the comet would evaporate a substantial fraction of itself. That's a lot of mass loss. It should be visible. Astronomers should see a huge coma, a massive cloud of gas and dust enveloping the nucleus. The tail should be prominent. Spectroscopy should reveal abundant volatiles. Yet the observations so far show something more subtle. There are reports of a jet structure, possibly directed toward the sun, and the object's colour is unusual, bluer than expected. But a giant coma proportional to that level of mass loss hasn't been definitively observed yet. That doesn't mean the natural explanation is dead. Comets are variable. Outgassing can be episodic, driven by rotation, by the exposure of fresh ices, by the collapse of surface layers. Maybe the high mass loss rate was temporary, a burst near perihelion that has since subsided. Maybe the gas is escaping in a concentrated jet rather than spreading uniformly, making the coma less obvious from Earth. Maybe the composition is such that the gas is transparent or doesn't carry much dust, reducing visibility. The bluer than the sun colour is intriguing. It might indicate ionized carbon monoxide, a molecule that can dominate the spectrum of certain comets. Carbon monoxide ice is more volatile than water ice, sublimating at lower temperatures and greater distances from the sun. An interstellar comet might have a different composition than solar system comets, richer in carbon monoxide or other exotic ices, because it formed in a different stellar environment. Some images show what might be an anti-tail, a feature pointing toward the sun rather than away from it. This is rare but not impossible. It can happen due to the geometry of observation, where we're looking at the comet from an angle that makes dust in the orbital plane appear to point forward, or it could be a genuine forward jet, driven by rotation or localized heating. The natural explanation requires all these pieces to fit together: high mass loss, unusual composition, episodic outgassing, geometric effects. It's a complicated picture, but comets are complicated objects. They don't all behave the same way. An interstellar comet, formed in another star system with different conditions, could easily deviate from the patterns we see in solar system comets. There's also the matter of the object's size and mass. Estimates suggest a diameter of at least several kilometers, possibly 5 or more, and a mass exceeding 30 billion tons. That's a big comet. Accelerating a body that massive through outgassing requires tremendous energy and material loss. It's like trying to push a cargo ship by throwing cargo overboard. You can do it, but you need to throw a lot of cargo very fast. Analogies help here. Imagine a massive container ship losing half its cargo over a month to speed up slightly. It's possible, but dramatic. You'd expect to see containers floating everywhere, debris fields, evidence of the loss. Similarly, if 3i Atlas is losing 1/6 of its mass in a month, we should see evidence: gas, dust, a glowing envelope. What would satisfy the natural explanation? Detection of a large coma, consistent with the predicted mass loss rate. Spectroscopy confirming the presence of water, carbon monoxide, carbon dioxide, or other volatiles in the expected quantities. Imaging showing a classic cometary structure, tail, maybe multiple jets. And most importantly, the acceleration should correlate with distance from the Sun. As the comet moves away from perihelion, solar heating decreases, outgassing should weaken, and the acceleration should drop. If it doesn't, if the acceleration persists or even increases as the comet moves farther from the Sun, that's a red flag. Right now, the natural outgassing hypothesis is plausible but strenuous. The required mass loss rate is high. The observational evidence is ambiguous. The object's size and mass make the story more difficult, but comets have surprised us before. Oumuamua surprised us with its acceleration and elongated shape. Borisov surprised us by looking entirely normal. 3i Atlas might just be the next surprise, a comet with extreme characteristics that push the boundaries of what we consider typical. Or it might be something else entirely. That's what we explore next, the exotic technological hypotheses that sit on the edge of speculation and science. Part 7, Non-Gravitational Acceleration, Exotic Technological Hypotheses. What if the acceleration isn't natural? What if 3i Atlas isn't just a comet doing comet things? What if it's something engineered, something sent, something designed? Avi Loeb and his colleagues have published a paper titled, "Is the Interstellar Object 3i Atlas Alien Technology?" It's not a joke. It's a serious scientific inquiry, framed within the context of what we can and cannot rule out. The paper considers the possibility that the object is a technological artifact, perhaps a probe from another civilization. Why would anyone suggest this? Several factors converge. First, the non-gravitational acceleration. If it's not outgassing, or if the outgassing explanation strains credulity due to the required mass loss rate, then we need alternative mechanisms. Second, the size and mass estimates. A large, massive object experiencing measurable acceleration implies significant energy and momentum transfer. Third, the trajectory. Loeb notes that the object's path through the inner solar system, its timing, and its alignment with the plane of Earth's orbit are statistically unusual. Not impossible, but unlikely if it's a random visitor from interstellar space. The energetics are worth exploring. For an object with a mass of tens of billions of tons to sustain an acceleration of 0.02 millimeters per second squared for weeks, the required thrust is substantial. Force equals mass times acceleration. Plug in 10 to the 13 kilograms and 2 times 10 to the negative 5 meters per second squared, and you get a force of about 200,000 newtons. That's the thrust of a small rocket engine, sustained continuously. If the mechanism is artificial, it implies a propulsion system, maybe a solar sail, using the pressure of sunlight to accelerate. But solar sails are inefficient unless they're very large and very reflective. Calculations suggest a sail large enough to accelerate this mass would need to be kilometers across and oriented correctly, or maybe something more exotic, an ion drive, a fusion engine, or a technology we haven't invented yet. The 1.4 GHz pings mentioned in the social media post add another layer to this: hypothesis. 1.4 GHz is significant in the search for extraterrestrial intelligence because it corresponds to the hydrogen line, a natural frequency emitted by neutral hydrogen atoms. It's sometimes called the waterhole in radio astronomy, a quiet band in the electromagnetic spectrum where signals could travel through space with minimal interference. If an advanced civilization wanted to send a signal, 1.4 GHz would be a logical choice. But here's the problem. There's no publicly verified detection of such pings from 3i Atlas. Radio telescopes monitor the sky constantly, and if there were a strong structured signal coming from the object, someone would have noticed. The claim remains unsubstantiated, floating in the realm of speculation. Still, let's entertain the hypothesis. Suppose 3i Atlas is an artificial probe. What would its purpose be? Reconnaissance? Observation? Maybe it's been drifting through space for millions of years, a relic from a long-dead civilization, still carrying out its programmed mission to survey star systems. Or maybe it's active, deliberately adjusting its course to study interesting targets. Could it intentionally steer itself to intercept Earth? The short answer is yes, if it has the capability. A probe with a functioning propulsion system could, in principle, alter its trajectory. But the delta V required to convert a 270 million kilometre miss into an actual intercept is far more than 86 metres per second. You'd need velocity changes on the order of kilometres per second, applied with precise timing and direction. That's a lot of thrust sustained over a long period. Loeb has also discussed the dark forest hypothesis in relation to 3i Atlas. The dark forest idea, popularised by the science fiction author Liu Cixin, suggests that the universe is full of civilizations, but they remain silent to avoid detection by potentially hostile neighbours. Revealing your presence could invite destruction, so everyone stays quiet, hiding in the cosmic dark forest. Loeb speculates that if 3i Atlas is a probe, its behaviour might reflect a cautious approach, observing from a distance rather than making direct contact. This is highly speculative. Multiple layers of assumption are piled on top of each other. Assumption 1, the acceleration isn't natural. Assumption 2, it's artificial. Assumption 3, it's controlled by an intelligence. Assumption 4, that intelligence is cautious or intentional in its approach to Earth. Each assumption reduces the probability of the overall scenario. What would count as a smoking gun for technological origin? Several things come to mind. Unexpected radio emissions, especially structured signals with information content. Non-volatile thrust signatures, meaning sustained acceleration with no corresponding mass loss or gas release. Extremely low mass loss with high acceleration, violating the physics of rocket propulsion unless there's an external energy source. Highly reflective surfaces, suggesting manufactured materials rather than natural rock and ice. Changes in attitude or orientation that can't be explained by rotation or tumbling. If observations detect any of these, the conversation changes immediately. Suddenly, the exotic hypothesis isn't fringe speculation anymore. It's a viable explanation demanding investigation. But if none of these signatures appear, if the object continues to behave like a weird but natural comet, then the technological hypothesis fades back into the background. The stakes are enormous if the probe scenario is true. It would confirm we're not alone. It would mean another civilization reached a level of technology sufficient to send objects across interstellar space. It would raise questions about their intentions, their longevity, their fate. Are they still out there? Did they send one probe or 1,000? Is 3i Atlas ancient or recent? But the stakes being high doesn't make the hypothesis true. Extraordinary claims require extraordinary evidence, and right now, the evidence is ambiguous at best. The non-gravitational acceleration is real, but it's not definitively non-natural. The trajectory is unusual, but not impossible for a random interstellar object. The radio pings are unverified. The lack of a massive coma is suggestive, but not conclusive. Science proceeds by testing hypotheses, by making predictions and checking them against observations. The technological hypothesis makes predictions too. No large gas cloud, because there's no outgassing. Persistent acceleration even as the object moves away from the sun, because the propulsion isn't solar-driven. Possible radio emissions or other non-thermal signatures. Over the next few months, observations will test these predictions. If the object turns out to be natural, we've still learned something valuable. We've pushed the boundaries of cometary science, explored the chemistry and dynamics of interstellar visitors, and tested our models against an extreme case. If the object turns out to be artificial, well, that's the biggest discovery in human history. Either way, the observations coming in late 2025 and early 2026 will be fascinating. Next, we turn to how this story spread, how social media took scientific data and wove it into a narrative of alien interception and conspiracy. Part 8, the social media narrative and conspiratorial framing. The posts appeared on X in mid-October 2025. An independent researcher, not affiliated with any major institution, laid out a series of claims. The core was simple. 3i Atlas is accelerating. If it keeps accelerating at 0.02 millimeters per second squared for 50 days, it will gain 86 meters per second of velocity. That velocity change, applied in the right direction at the right time, could line the object up with Earth on December 19, 2025. Then the claims escalated. The researcher suggested the acceleration wasn't random, it was intentional. The object was maneuvering, course-correcting, aiming itself toward Earth. There were mentions of 1.4 GHz pings detected near Mars, alleged communications, handshakes between the object and something else. The narrative shifted from interesting scientific anomaly to alien probe is targeting us. Let's break this down piece by piece. The data, the part about the acceleration, that's real. Avi Loeb reported it. It's based on astrometric observations from reputable sources. The arithmetic, the calculation that 0.02 millimeters per second squared times 50 days equals 86 meters per second, that's correct too. Basic physics, no errors there. But then come the assumptions. The assumption that the acceleration persists for exactly 50 days. The assumption that it's directed toward Earth. The assumption that the timing aligns perfectly with Earth's position in orbit. None of these are verified. They're extrapolations, guesses based on limited data. The interpretation, the claim that the object is lining up with Earth, that's where data ends and narrative begins. Lining up implies intent. It implies the object is steering itself deliberately toward our planet. There's no evidence for that. The missed distance is still 270 million kilometers. NASA says no threat. The geometry doesn't support an intercept scenario unless multiple unlikely factors align. The 1.4 GHz pings? Unverified. No major observatory has confirmed radio emissions from 3i Atlas. If such a signal existed, radio astronomers would be all over it. The lack of confirmation doesn't prove the pings didn't happen, but it means we can't take them seriously without evidence. So how did this narrative gain traction? Social media thrives on uncertainty and drama. A scientific anomaly, a gap in our understanding, becomes fertile ground for speculation. People take the data, add their own interpretations, and create stories. Those stories spread faster than the science because they're more exciting. An alien probe targeting Earth is a better headline than Comet shows unusual outgassing. The psychology here is fascinating. Humans are pattern-seeking creatures. We see connections even when none exist. We're drawn to narratives that give meaning to chaos. An interstellar object with an unexplained acceleration isn't just a comet behaving oddly. It's a sign, a message, maybe a warning. The claim fits into larger cultural anxieties about the unknown, about what's out there, about whether we're prepared for contact. Conspiratorial framing amplifies this. Once the seed is planted that the object might be artificial, every ambiguity becomes evidence. The lack of a visible coma, proof it's not a comet. The unusual colour, engineered materials, the trajectory, deliberate targeting, the lack of official confirmation of the radio pings, a cover-up obviously. The narrative becomes self-reinforcing, immune to contradiction. This isn't unique to 3i Atlas. Oumuamua went through the same cycle. A weird object appears, scientists admit they don't fully understand it, and the internet fills the gaps with aliens. Sometimes the scientists themselves, like Avi Loeb, lean into the speculation. Loeb is known for entertaining exotic hypotheses publicly, arguing that we should consider all possibilities, including technological origins. That openness is valuable in science, but it also provides ammunition for sensationalism. Mainstream media picks up the story, often in simplified or exaggerated form. Headlines scream, "Alien probe," even when the article itself is more measured. The New York Post ran a piece quoting Loeb on 3i Atlas, framing it as a potential alien engine. The framing matters. Most people don't read past the headline. They absorb the idea that scientists think it might be aliens, and that becomes the story. The responsibility in science communication is to distinguish between here's what the data show and here's what someone extrapolates. The data show a non-gravitational acceleration, full stop. The extrapolation to Earth intercept, to intentional maneuvering, to alien technology, those are interpretations layered on top. They might be true, but they're not established facts. There's a balance to strike. On one hand, we shouldn't dismiss possibilities prematurely. Science advances by considering ideas that seem unlikely. On the other hand, we shouldn't treat speculation as equivalent to evidence. The claim that 3i Atlas is lining up with Earth is not on the same footing as the observation that it has a non-gravitational acceleration. One is measured, the other is inferred. Social media collapses that distinction. Everything becomes a claim, a theory, a possibility. The signal-to-noise ratio deteriorates. People argue about whether the object is a threat without agreeing on what the data actually say. Misinformation spreads not because people are lying, but because the line between data and interpretation gets blurred. So where does that leave us? With a meta-question. Are we prepared for the possibilities? What if the object is natural but genuinely weird, pushing the boundaries of cometary physics? What if it is artificial, confirming we're not alone? How do we, as a society, process information in a landscape where truth and speculation coexist on the same feed? The social media narrative around 3i Atlas is a case study in how science and storytelling intersect. The next part explores what happens if the story turns out to be more than just a story, if the object actually did something unexpected. Part 9, If it intersected, worst-case hypotheses. Let's engage in a thought experiment. This is scenario analysis, not prediction. What if all the assumptions held? What if 3i Atlas somehow managed to alter its course enough to intersect Earth? What would that mean? First, the parameters. Size estimates for 3i Atlas range from a few hundred meters to several kilometers in diameter. Some calculations, based on its brightness and assumed albedo, suggest it could be 5 kilometers across or even larger. Mass estimates exceed 30 billion tons, possibly more. That's a mountain, hurtling through space. Interstellar objects travel fast. When they enter a solar system on a hyperbolic trajectory, they're not bound by the sun's gravity, so they don't slow down much. 3i Atlas is moving at roughly 60 kilometers per second, 60,000 meters per second. That's over 130,000 miles per hour. At that speed, kinetic energy scales dramatically. The kinetic energy formula is simple. Energy equals 1/2 times mass times velocity squared. Let's use a conservative estimate. Say the mass is 30 billion tons, which is 3 times 10 to the 13th kilograms. Velocity is 30,000 meters per second, a midpoint estimate. Plug those in. 1/2 times 3 times 10 to the 13 times 9 times 10 to the 8th. That gives you roughly 1.35 times 10 to the 22nd joules. How much energy is that? A megaton of TNT releases about 4.2 times 10 to the 15 joules. Divide the kinetic energy by that, and you get approximately 3.2 million megatons. 3 million megatons. For comparison, the largest nuclear weapon ever tested, the Soviet Tsar bomber, was 50 megatons. This impact would be 60,000 times more powerful. The consequences would be catastrophic. An object of that size and speed would punch through the atmosphere in seconds. It wouldn't have time to slow down or ablate significantly. It would hit the surface at nearly full speed, releasing all that kinetic energy in an instant. The explosion would dwarf anything in human history, natural or artificial. Firestorms would ignite across continents. The shockwave would flatten everything within hundreds of kilometers of the impact site. Earthquakes would ripple through the crust. If it hit an ocean, the tsunami would be thousands of meters high, traveling at jet speeds across ocean basins. Coastal cities would be obliterated. But the immediate destruction is only the beginning. The energy would vaporize the impactor and a huge volume of rock, soil, or water, sending it into the atmosphere. Dust and aerosols would spread globally within days, blocking sunlight. Temperatures would plummet. Photosynthesis would halt. Crops would fail. The resulting famine would kill more people than the initial impact. This is an extinction-level event. Not necessarily the extinction of all life. The Earth has survived worse, but the extinction of most large animals, including humans. We're talking about a scenario comparable to the impact that killed the dinosaurs 66 million years ago. Now, let's consider a less extreme case. Suppose 3i Atlas doesn't hit Earth, but passes much closer than the predicted 1.8 astronomical units. Say it passes at tens of thousands of kilometers, roughly the distance to geostationary satellites. What happens then? A close flyby would still be dramatic. The object's gravity would perturb Earth's orbit slightly, though probably not enough to notice. Earth is much more massive, so the effect would be minimal, but the electromagnetic and plasma interactions could be interesting. If the object has a magnetic field or carries charged particles, there might be auroras, radio disturbances, even temporary disruptions to satellites. There's also the question of debris. If 3i Atlas is shedding material, either through outgassing or fragmentation, a close flyby could inject dust and particles into Earth's atmosphere. Meteor showers could intensify. Spacecraft in low Earth orbit might be at risk from impacts. The International Space Station, satellites, everything in orbit would need to be monitored. From a scientific standpoint, a close flyby would be a bonanza. Telescopes would capture data at unprecedented resolution. Radar could map the surface. Spectroscopy could analyse the composition in detail. If the object turned out to be artificial, the evidence would be undeniable at close range. But let's return to the central question. How much delta V would actually be required to convert the predicted miss into an intercept? The miss distance is 270 million kilometres. To close that gap, you'd need to change the trajectory significantly. 86 metres per second isn't nearly enough unless the geometry is extraordinarily favourable. Let's do a rough estimate. The object's velocity is 60 kilometres per second. A 1% change in velocity is 600 metres per second. That might shift the miss distance by a few million kilometres, depending on direction and timing. To shift it by 270 million kilometres, you'd likely need a change of several kilometres per second, applied over weeks or months, in precisely the right direction. That's not happening with 0.02 millimetres per second squared over 50 days. You'd need a much stronger acceleration, sustained much longer, or applied much earlier in the trajectory. The numbers don't support an intercept scenario based on the reported acceleration. So the worst-case hypotheses are terrifying, but the chain of assumptions required to get there is long and fragile. The object would need to have a propulsion system capable of enormous thrust. It would need to have started manoeuvring months or years ago, not just near perihelion. It would need precise knowledge of Earth's position and velocity, and even then the energetics are daunting. If the object were artificial and targeting Earth, what would the intention be? Observation. Seems most plausible. Why send a probe across interstellar space only to destroy it and the target in a collision? A flyby makes more sense. Get close enough to study the planet, its atmosphere, its biosphere, maybe even its technological signatures, then move on. Alternatively, maybe it's not targeting Earth at all. Maybe the trajectory is coincidental, the product of dynamics in whatever star system it came from. We're reading intent into randomness, seeing patterns where none exist. What monitoring and defense options do we have? Not many at this point. Planetary defense systems like NASA's Double Asteroid Redirection Test, or DART, are designed for smaller, slower objects that we detect years in advance. An interstellar intruder moving at 60 kilometers per second, detected only months before closest approach, is beyond our current capability to deflect. Early warning networks help. If we detect the object years in advance, we might have time to plan a mission, maybe even intercept it for study. But 3i Atlas was discovered in July 2025, only months before its perihelion and Earth approach. That's not enough time to mount a deflection mission. So the worst-case scenario motivates preparedness, but it doesn't define our current situation. The reality is that 3i Atlas poses no threat, according to every credible orbital calculation. The miss distance is comfortable, the trajectory is well understood, agencies are monitoring it, but they're not sounding alarms. Next, we widen the lens to consider the broader implications of interstellar objects for planetary defense and the study of extrasolar systems. Part 10. Broader implications for interstellar objects, planetary defense. 3i Atlas is only the third confirmed interstellar object ever detected. The first was Oumuamua, discovered in October 2017. The second was Borisov, found in August 2019. Before that, we had no direct evidence that objects from other star systems ever visited ours. Now we know they do, and probably more often than we realised. the study of interstellar objects offers a unique window into the universe beyond our solar system. These are pieces of other worlds, debris from planetary systems light years away, delivered to our doorstep. By analysing their composition, structure and behaviour, we can learn about the chemistry and dynamics of star systems we'll never visit. Oumuamua was a mystery from the start. Its elongated shape, tumbling rotation, and slight non-gravitational acceleration sparked endless debate. Was it a comet? An asteroid? Something else? Spectroscopy revealed no coma, no tail, no obvious signs of outgassing. Yet it accelerated as it moved away from the Sun, suggesting some force beyond gravity. Avi Loeb famously suggested it might be a light sail, a thin reflective sheet pushed by solar radiation. Most astronomers disagreed, proposing instead that it was a comet with unusual properties, maybe composed of hydrogen ice or nitrogen ice that sublimates without leaving a visible cloud. Borisov was different. It looked like a normal comet. It had a coma, a tail, spectroscopic signatures of water and carbon monoxide. It behaved exactly as expected for an icy body passing close to the Sun. In many ways, Borisov was reassuring. It showed that not every interstellar object is weird. Some are just comets from somewhere else. 3i Atlas falls between these extremes. It shows some cometary features, but also anomalies that don't fit neatly into standard models. The non-gravitational acceleration is stronger than expected for its size. The mass loss rate, if it's due to outgassing, is extreme. The colour and possible anti-tail add further quirks. What does this tell us about interstellar objects in general? That they're diverse, that we can't assume they all behave like solar system comets or asteroids. That composition, structure and history vary depending on where and how they formed. The dynamics of interstellar objects also challenge our understanding. How often do they visit? Where do they come from? Are they ejecta from planetary systems, kicked out by gravitational interactions with giant planets? Or are they remnants of star formation, leftover material that never coalesced into planets? Detection rates suggest interstellar objects pass through the inner solar system more frequently than we thought. With better telescopes and more sky surveys, we're finding them. 3i Atlas was spotted by the same system that looks for near-Earth asteroids. Future surveys, like the Vera C. Rubin Observatory, will detect many more. We might be finding 1 or 2 per year within a decade. This brings us to planetary defence. While 3i Atlas poses no current threat, the fact that extrasolar bodies can cross our solar system means future ones might come closer. Detection and response capability must improve. Planetary defence against interstellar objects is harder than against solar system objects for several reasons. First, speed. Interstellar objects travel much faster, tens of kilometres per second instead of a few. That gives less time to react and makes deflection more difficult. Second, unpredictability. We don't know their orbits until they're already here. Solar system objects follow predictable paths we can track for years. Interstellar visitors appear suddenly. Third, limited observation windows. They pass through quickly and fade from view. We might have only months to study them. Mission design becomes critical. If we detect an interesting interstellar object years before its closest approach, could we send a spacecraft to intercept it? The answer is maybe, depending on the trajectory and our readiness. Missions like the European Space Agency's Comet Interceptor are designed to respond quickly to transient targets. More missions like that, pre-positioned in space, waiting for a target to appear, could revolutionize our ability to study interstellar visitors. Advanced radar and optical tracking would help too. Better astrometry means more precise orbits, which means earlier detection of potential threats and better characterization of interesting objects. Artificial intelligence can assist, sifting through vast datasets to flag anomalies and predict trajectories. There are technological spin-offs as well. Modelling high-velocity objects improves our understanding of impact physics, which has applications in materials science and planetary geology. Tracking faint, fast-moving objects pushes the limits of instrumentation and data processing. These advances benefit not just planetary defence but astronomy more broadly. Now consider the implications if 3i Atlas turns out to be artificial. The impact on the search for extraterrestrial intelligence would be enormous. SETI has been listening for radio signals for decades, searching for deliberate transmissions from other civilizations. But an interstellar probe, a physical object sent across the galaxy, represents a different mode of communication and exploration. It suggests a civilization that built machines, launched them into space, and either still exists or has left these relics behind. If 3i Atlas is natural but weird, the implications for solar system formation and extrasolar chemistry are still massive. It means the diversity of small body physics is greater than we understood. It means our models of comets, asteroids, and planetesimals need to account for a wider range of compositions and behaviours. Either way, 3i Atlas is a wake-up call. Whether the story ends with a confirmed comet or a revolutionary discovery, the object reminds us that our solar system is not isolated. The galaxy is vast, filled with countless stars and planets, and the space between them is not empty. Objects drift, collide, escape, and wander. Some of them end up here. Public fascination with alien probes can draw attention and funding to space science, but it also risks miscommunication. Planetary defense agencies must manage both data and narrative, providing accurate information while acknowledging uncertainty. The line between responsible speculation and sensationalism is thin. Scientists like Avi Loeb walk that line deliberately, arguing that we should remain open to all possibilities. Critics argue that entertaining exotic hypotheses without sufficient evidence undermines public trust in science. The debate is healthy. It reflects the tension between caution and curiosity, between conservatism and imagination. 3i Atlas, regardless of what it turns out to be, embodies that tension. Next, we shift to recent breakthroughs in other areas of space science that connect to this story. Part 11. Recent breakthrough in exoplanet atmosphere imaging. 2025 has been a golden year for exoplanet science. The James Webb Space Telescope, launched in late 2021, has spent years refining its instruments and targeting distant worlds. This year, it captured something extraordinary: detailed molecular signatures in the atmosphere of a Neptune-sized exoplanet orbiting a star 60 light-years away. The planet, designated K218b, had been studied before, but JWST's infrared capabilities allowed astronomers to probe deeper into its atmosphere than ever before. The spectrum revealed water vapour, methane, carbon dioxide, and hints of dimethyl sulfide, a molecule on Earth produced primarily by biological processes. The detection is tentative, requiring more observations to confirm, but if it holds up, it's the first potential biosignature in an exoplanet atmosphere. Why does this matter for 3i Atlas? Because the same techniques used to analyse exoplanet atmospheres apply to studying the comas and jets of comets. Spectroscopy, the splitting of light into its component wavelengths, tells us what molecules are present. Whether you're looking at a planet 40 parsecs away or a comet 2 astronomical units away, the method is the same. We live in an era where we can peer at the atmospheres of distant worlds and dissect the chemistry of interstellar visitors. The tools overlap. The instruments that scrutinise exoplanets during transits, when they pass in front of their host stars, can also be turned toward 3i Atlas to analyse its coma, jets, and any gases it's releasing. The exoplanet result from 2025 underscores the power of modern astrochemistry. Decades ago, we could barely detect exoplanets, let alone characterise their atmospheres. Now we're identifying individual molecules, assessing habitability, searching for signs of life. That same capability applies closer to home. 3i Atlas might offer a sample of extrasolar material, a direct probe of the chemistry in another star system. Its anomalous features, the acceleration, the unusual colour, the possible anti-tail, make it a wild card. If its composition turns out to be exotic, rich in molecules we don't see in solar system comets, it tells us about the diversity of planetary formation across the galaxy. The cross-disciplinary nature of this work is striking. Planetary science, astronomy, instrumentation, chemistry, physics, all converge. The same scientists analysing exoplanet spectra might collaborate with those studying 3i Atlas. The same telescopes serve both purposes. Let's consider a specific case study. The detection of water vapour and methane in K218b's atmosphere involved observing the planet multiple times as it transited its star. Each transit provided a spectrum, showing which wavelengths of light were absorbed by the atmosphere. By comparing spectra, astronomers identified absorption lines corresponding to specific molecules. The precision required is extraordinary. We're talking about detecting parts per million of molecules in an atmosphere hundreds of trillions of kilometers away. Could similar techniques detect signatures of artificiality in 3I Atlas? Possibly. If the object has a metallic surface, engineered materials, or unusual reflectivity, spectroscopy might reveal it. Metals have distinct spectral signatures. A surface covered in aluminum or steel would reflect light differently than rock and ice. Polymers, ceramics, other manufactured substances all have fingerprints in the spectrum. If 3I Atlas were a probe, a spacecraft of some kind, its surface materials might betray its origin. Natural objects are made of silicates, organics, ices. Artificial objects might include alloys, composites, coatings designed for durability in space. The difference should be detectable, assuming we get high-resolution spectra. The same telescopes scanning distant worlds help us scrutinize nearer interstellar intruders. JWST, Hubble, ground-based observatories with adaptive optics all contribute. The synergy between exoplanet science and solar system science is one of the underappreciated aspects of modern astronomy. There's also a philosophical connection. Studying exoplanets is about understanding our place in the universe, about finding other worlds that might harbour life. Studying interstellar objects is about encountering pieces of those worlds, about receiving visitors from systems we'll never reach. Both endeavours are driven by the same question: are we alone? If 3I Atlas is natural, it's still a messenger from another star, carrying information about its birthplace. If it's artificial, the implications are obvious. Either way, it connects to the broader search for life and intelligence beyond Earth. Coming up, we examine recent discoveries in dark matter and modified gravity theories, which might relate to how we interpret anomalous accelerations in small bodies like 3I Atlas. Part 12. New discovery in dark matter or modified gravity. Earlier this year, astronomers announced results from the Vera C. Rubin Observatory, which began operations in 2024. The observatory conducts the legacy survey of space and time, imaging the entire southern sky every few nights. One of its goals is to map the distribution of dark matter by observing how galaxies cluster and how light bends around massive structures. A recent result showed discrepancies in galactic rotation curves that don't quite match standard dark matter models. Rotation curves describe how fast stars orbit the centre of a galaxy at different distances. In a galaxy with only visible matter, stars farther out should orbit slower, following Kepler's laws, but observations show they orbit just as fast as stars closer in, suggesting there's more mass than we can see. That unseen mass is called dark matter. The new data from Rubin Observatory suggests the distribution of dark matter in some galaxies is lumpier or more diffuse than models predicted. This could mean our understanding of dark matter is incomplete, or it could hint at modified gravity theories, alternatives to general relativity that explain galactic dynamics without invoking unseen matter. The implications are profound. Dark matter supposedly makes up about 85% of all matter in the universe, yet we've never seen it directly. We infer its presence from gravitational effects, from the way galaxies rotate, from how light bends around galaxy clusters, from the structure of the cosmic microwave background. But we don't know what it's made of. Decades of experiments searching for dark matter particles, weakly interacting massive particles or WIMPs, have come up empty. The detectors sit deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with an atomic nucleus. So far, nothing definitive. The Rubin Observatory data add another layer of uncertainty. If dark matter's distribution doesn't match our models, maybe we're missing something fundamental about how it behaves. Or maybe, and this is the more radical possibility, dark matter doesn't exist at all. Maybe gravity itself works differently on large scales than we think. Modified gravity theories, like modified Newtonian dynamics or MOND, propose that Newton's laws break down when gravitational acceleration becomes extremely weak, as it is in the outer regions of galaxies. Instead of invoking unseen matter, these theories tweak the equations of motion. They've had some success explaining galactic rotation curves without dark matter, but they struggle with other observations like gravitational lensing and the cosmic microwave background. The debate between dark matter and modified gravity has raged for decades. Most physicists favour dark matter because it fits more observations and integrates better with our understanding of particle physics and cosmology. But the persistent lack of direct detection keeps modified gravity theories alive. What does this have to do with 3I Atlas? When we observe a non-gravitational acceleration in an object like 3I Atlas, we're assuming our model of gravity is correct. We calculate where the object should be based on the Sun's gravity, the planet's gravity, and relativistic effects. Any deviation from that prediction is labelled non-gravitational, meaning it's due to something other than gravity. But what if our gravity model is slightly wrong? What if there are small corrections, unaccounted forces, or subtle effects we haven't discovered yet? Then what we interpret as a thrust or outgassing might actually be a misunderstanding of the underlying physics. This is a long shot, but it's worth considering. Historically, anomalies in orbital mechanics have led to new physics. The precession of Mercury's orbit, the slow rotation of its elliptical path, couldn't be explained by Newtonian gravity. Einstein's general relativity solved it, showing that space-time curvature near the Sun caused the effect. Could the anomalies in small body trajectories hint at something similar? Probably not. The scales are different. Dark matter and modified gravity theories operate on galactic scales, where gravitational fields are weak and distances are vast. The inner solar system, where 3I Atlas is moving, has strong gravitational fields dominated by the Sun. Corrections from modified gravity would be tiny, far smaller than the observed acceleration. To put this in perspective, the gravitational acceleration at Earth's distance from the Sun is about 6 millimeters per second squared. At 3I Atlas's perihelion distance of roughly 1.4 astronomical units, it's even stronger. Modified gravity theories predict deviations from Newtonian gravity when accelerations drop below about 10 to the negative 10 meters per second squared, 100 million times weaker than what 3I Atlas experiences. So any modified gravity effect would be utterly negligible here. Still, the recent discovery in dark matter research reminds us that our understanding of gravity and mass is incomplete. We don't know what dark matter is. We've never detected a dark matter particle directly. We infer its existence from gravitational effects, but we don't understand its nature. The mystery deepens when you consider the cosmological scale. The universe's expansion is accelerating, driven by something we call dark energy. Like dark matter, we don't know what it is. It makes up about 68% of the universe's energy density, yet it's completely invisible and detectable only through its gravitational effects. So roughly 95% of the universe, dark matter plus dark energy, is made of things we don't understand. If our models of mass distribution are incomplete, could we be mismodeling small force accelerations? Could radiation pressure, drag from interplanetary medium, or interactions with the solar wind be stronger than we think? These are natural forces, not requiring exotic physics, but they might be underestimated. Radiation pressure from sunlight pushes on objects in space. The effect is tiny for large massive bodies, but can be significant for small particles or objects with large surface areas relative to their mass. Astronomers account for this when calculating orbits, but the calculations depend on knowing the object's size, shape, and reflectivity. If those parameters are uncertain, the radiation pressure estimates could be off. The Yarkovsky effect is another subtle force. When a rotating object absorbs sunlight, it heats up. The heated side radiates that energy as infrared light, creating a tiny thrust. Over time, this can alter an object's orbit measurably. Asteroids drift slowly inward or outward over millions of years due to the Yarkovsky effect. Again, astronomers model this, but it requires knowing the object's thermal properties, rotation rate, and surface composition. Drag from the interplanetary medium is even more subtle. Space isn't a perfect vacuum. There's a sparse plasma of charged particles streaming outward from the sun and the solar wind. Objects moving through this medium experience a tiny drag force. For most objects it's negligible, but for something as large and fast as 3I Atlas, could it matter? The 0.02 millimeters per second squared acceleration of 3I Atlas is tiny. It's on the edge of what we can measure reliably. Small systematic errors in astrometry, slight mismodelling of planetary perturbations or unaccounted forces could mimic a non-gravitational acceleration. Astrometry, the precise measurement of an object's position in the sky, is challenging. You're tracking a faint dot moving against the background of stars, trying to pinpoint its location to fractions of an arc second. Atmospheric turbulence blurs the image. Telescope imperfections introduce distortions. Timing uncertainties add noise. Even with the best instruments, there's measurement error. When you fit an orbit to astrometric data, you're solving a complex equation that balances gravitational forces from the Sun, planets, and sometimes even large asteroids. If the measurements have small systematic biases, if the timestamps are slightly off, if the star catalogue you're using to define positions has errors, the fitted orbit will have residuals. Those residuals might look like a non-gravitational acceleration when they're really just noise. That said, astronomers are careful. They account for known forces. They model solar radiation pressure, the Yarkovsky effect, where absorbed sunlight creates a small thrust, planetary gravity, relativistic effects. If they report a residual acceleration, it means those factors don't explain the observation. The Jet Propulsion Laboratory and the Atacama Large Millimeter Array, the sources of the astrometry data Avi Loeb cited, are world-class facilities. Their measurements are trustworthy. The 4 arc-second offset Loeb mentioned is significant, well above the noise level. So the non-gravitational acceleration is probably real, not an artifact of bad data. But the interpretation of that acceleration, what's causing it, remains open. Outgassing is the default explanation, but as we've discussed, it requires a high mass loss rate that hasn't been definitively observed. Could there be another natural mechanism we're overlooking? One possibility is fragmentation. If 3I Atlas is breaking apart, shedding pieces as it heats up, the ejected fragments carry momentum. The reaction force accelerates the main body. This is similar to outgassing, but driven by mechanical breakup rather than sublimation. Comets occasionally fragment, especially when stressed by tidal forces or rapid rotation. If 3I Atlas is a rubble pile, a loose collection of rocks and ice barely held together by gravity, it might be unstable. Another possibility is electrostatic effects. Objects in space can build up electric charge from the solar wind and cosmic rays. If the charge distribution is asymmetric, interactions with the interplanetary magnetic field could produce small forces. This is speculative, and the effect would be tiny, but it's a natural mechanism that doesn't require outgassing or propulsion. The link between 3I Atlas and dark matter is speculative, a hook for viewers to consider the boundary between known and unknown physics. Could an interstellar object harness some form of propulsion or reaction to an unknown ambient medium? If our gravity and mass models are incomplete, could non-gravitational acceleration mean something different than we think? Imagine if there were a fifth force, something beyond gravity, electromagnetism, and the strong and weak nuclear forces. Physicists have searched for fifth forces for decades, conducting precision experiments to test whether gravity behaves exactly as general relativity predicts. So far, no deviations have been confirmed, but the possibility remains tantalizing, especially at scales or in regimes we haven't fully explored. An interstellar object like 3I Atlas, coming from a different environment, might interact with forces or fields we haven't encountered in solar system objects. Its composition, forged in another star system under different conditions, might include elements or structures that respond to the interplanetary medium in unexpected ways. These are provocative questions, but they shouldn't distract from the more mundane explanations. Outgassing is still the leading hypothesis. The object is probably a comet with unusual properties, not a manifestation of new physics. The beauty of science is that we don't have to guess. Observations will decide. If 3I Atlas shows all the hallmarks of a comet, massive outgassing, a coma, spectroscopic signatures of volatiles, then the acceleration is explained. If it doesn't, if the anomalies persist without a clear natural mechanism, then we open the door to more exotic possibilities. The connection to dark matter and modified gravity is more philosophical than practical. It reminds us that our picture of the universe is incomplete. We're still learning, still discovering, still revising our models. 3I Atlas, whatever it turns out to be, is a data point in that ongoing process. Next, we explore how artificial intelligence is transforming the way we predict orbits and detect anomalies, which might shed light on 3I Atlas's true nature. Part 13, AI-driven astrometric orbit prediction tools. Artificial intelligence is changing how we study the cosmos. Machine learning algorithms can process vast amounts of data, identify patterns, flag anomalies, and make predictions faster and more accurately than traditional methods. In 2025, several new AI-driven tools were released for astrometry and orbit prediction, and they're already making an impact. One example is OrbNet, a neural network developed by a collaboration of universities and space agencies. OrbNet ingests astrometric data, observations of an object's position over time, and compares them to a purely gravitational model. It outputs residuals, the differences between observed and predicted positions, and flags objects with significant deviations. OrbNet was trained on decades of asteroid and comet data. It learned what normal looks like and what doesn't. When it encounters an object like 3I Atlas, with a measurable non-gravitational acceleration, it doesn't just flag it. It suggests potential causes based on patterns it's seen before. Outgassing, fragmentation, collisions, radiation pressure, even unknown thrust. Why does this matter? Because subtle deviations in trajectory can be missed or mismodeled by classic methods. Humans fitting orbits to data might overlook small residuals, attributing them to noise. AI, with its ability to analyze thousands of parameters simultaneously, can pick up patterns that escape notice. For 3I Atlas, AI systems are refining the orbit, detecting small-scale thrust vectors, and helping rule out or confirm maneuver hypotheses. If the object's acceleration changes over time, if it varies with distance from the Sun, if it shows directionality inconsistent with outgassing, AI will catch it. Another tool, called AstroAI, was released by the European Space Agency this year. It uses reinforcement learning to predict future positions of near-Earth objects and interstellar visitors. By training on historical data and simulating millions of possible trajectories, it can estimate how much correction would be needed to achieve specific outcomes, like aligning with a particular target. Researchers have already used AstroAI to analyze 3I Atlas. They input the observed acceleration, the current orbit, and Earth's position. The AI ran simulations asking what velocity change, applied when and in what direction, would result in an Earth intercept on December 19th. The answer came back clear. The required delta V is far larger than 86 meters per second. You'd need several kilometers per second, applied months earlier, with precise vectoring. The social media claim doesn't hold up under rigorous modelling. This is where AI excels. It can explore parameter space, testing thousands of scenarios in seconds. A human astronomer might calculate one or two scenarios by hand. AI calculates them all and identifies which are physically plausible. But AI has limitations. It's only as good as its input data. If the astrometric observations have systematic errors, if the object's motion is more complex than the model assumes, AI can produce misleading results. It can flag anomalies that aren't real, or miss subtle effects that aren't in its training data. Also, AI can identify correlations but not always causation. It might notice that the acceleration correlates with solar distance, suggesting outgassing. But it can't tell you definitively what chemical process is driving it. That requires spectroscopy, imaging, and human interpretation. The role of AI in the 3I Atlas investigation is supportive, not definitive. It helps refine orbits, detect patterns, rule out implausible scenarios, but the final judgment, whether the object is natural or artificial, comet or probe, rests on observational evidence and scientific reasoning. There's another dimension to AI in astronomy that's worth mentioning: pattern recognition in radio signals. The search for extraterrestrial intelligence generates enormous amounts of data. Radio telescopes scan the sky, recording signals across millions of frequency channels. Most of what they detect is noise, human-made interference, or natural astrophysical sources. Finding a genuine techno-signature, an artificial signal from another civilization, is like finding a needle in a haystack the size of a galaxy. AI helps. Algorithms trained to recognize patterns in noise can flag candidate signals for human review. They can filter out terrestrial interference, identify frequency drifts consistent with a transmitter on an orbiting or moving platform, and detect modulation patterns that suggest information content. If 3I Atlas were emitting radio signals, the 1.4 GHz pings claimed in the social media posts, AI would likely detect them. The fact that no major observatory has reported such signals despite continuous monitoring of the sky is strong evidence they don't exist. AI doesn't miss things like that. If there were a structured radio emission from the object's direction, it would have been flagged, analysed, and either confirmed or explained as interference. So the predictions from AI-driven orbit analysis are that by late 2025 and early 2026, we'll have definitive updates on 3I Atlas's trajectory. The residuals will be quantified with high precision. Any persistent acceleration will be mapped in 3 dimensions. Timing correlations with solar distance, rotation, or other factors will be identified. And the maneuver hypothesis, the claim that it's steering toward Earth, will be ruled in or out with confidence. The transparency of AI tools also helps with public trust. Results can be reproduced, checked, and verified by independent researchers. Unlike proprietary models or closed-door calculations, open-source AI platforms allow anyone with the data to run their own analysis. This democratizes science, making it harder for misinformation to take root. Next, we move into advances in radio astronomy, especially the 1.4 GHz band, and what they mean for detecting possible technosignatures from objects like 3I Atlas. Part 14. Advances in deep space radio astronomy, 1.4 GHz and beyond. Radio astronomy has had a remarkable year. In early 2025, the Breakthrough Listen project, a major initiative searching for technosignatures, released results from a survey covering millions of stars across the 1.2 to 1.8 GHz band. This range includes the 1.4 GHz hydrogen line, a natural frequency considered a prime channel for interstellar communication. The survey found no confirmed technosignatures, but it placed stringent constraints. If civilizations are broadcasting powerful radio signals at 1.4 GHz within a few thousand light-years of Earth, we would have detected them. The silence is informative. It suggests either intelligent civilizations are rare, they don't broadcast in this band, their signals are too weak for us to detect, or they're deliberately staying quiet. Advances in signal processing, larger arrays, and AI-driven filtering have made radio astronomy more sensitive than ever. The Meerkat array in South Africa, the Very Large Array in New Mexico, and the soon-to-be-completed square-kilometre array will push sensitivity even further. We're entering an era where detecting faint radio emissions from nearby stars or passing objects is not just possible, but routine. This brings us to the social media claim about 1.4 GHz pings from 3I Atlas. The claim suggests the object emitted structured signals near Mars, possibly handshakes or course correction communications. The frequency choice, 1.4 GHz, is significant. It's in the waterhole, a quiet part of the radio spectrum where galactic background noise is minimal and signals can propagate efficiently. If an advanced civilization wanted to send a signal that others could detect, 1.4 GHz would be a logical choice. It's universal. The hydrogen line is the same everywhere in the universe. Any civilization with radio astronomy would recognize it. But here's the problem. No public, peer-reviewed detection of such signals from 3I Atlas exists. Radio telescopes monitor the sky constantly. Projects like Breakthrough Listen specifically search for transient signals, bursts, and anomalies. If 3I Atlas were emitting 1.4 GHz pings strong enough to be detected on Earth or near Mars, someone would have noticed. Could the signals be too weak? Possibly. Radio signals weaken with distance according to the inverse square law. At a distance of 1 or 2 astronomical units, a weak transmitter might be below detection thresholds, but then it wouldn't be detectable near Mars either, which is where the social media posts claim the pings originated. Could the signals be intermittent, brief bursts that were missed? Also possible. Radio observations are not continuous. Telescopes have limited observing time, and they're not always pointed at the right place at the right time. A short-duration burst could slip through the cracks. But the lack of any independent confirmation is a red flag. If the pings were real, multiple observatories should have detected them by now. The fact that none have suggests the claim is unsubstantiated. Let's explore the plausibility from an engineering standpoint. Suppose 3I Atlas is an artificial probe. What would it take to send a 1.4 GHz signal detectable across interplanetary distances? Radio transmission requires power and an antenna. Power depends on the transmitter's design and energy source. An antenna's efficiency depends on its size and the wavelength of the signal. At 1.4 GHz, the wavelength is about 21 centimeters. A reasonably efficient antenna might be a few meters across, small enough to fit on a spacecraft. If the probe has a nuclear power source or some other long-lived energy supply, generating a few watts or kilowatts of radio power is feasible. That's enough to be detectable at distances of millions of kilometers, assuming a sensitive receiver and a directional antenna. But natural sources can also produce radio emissions. Comets, when they interact with the solar wind, can generate plasma instabilities that emit radio waves. Lightning in dust clouds, if they exist, could produce broadband radio bursts. These are rare, but possible. So even if a radio signal were detected from 3i Atlas, it wouldn't automatically mean the object is artificial. You'd need to analyse the signal structure, looking for modulation, repetition, frequency drift, anything that suggests information content rather than random noise. What should we watch for in the coming weeks? Upcoming radio astronomy observation campaigns are targeting the 3i Atlas region. Multiple observatories are coordinating, covering different frequency bands and times. Data release schedules will bring results in late 2025 or early 2026. SETI organisations are also paying attention. Breakthrough Listen has added 3i Atlas to its target list. If there's anything unusual in the radio spectrum, they'll find it. The role of radio astronomy in this investigation is to either confirm or rule out the technosignature hypothesis. If no signals are detected despite thorough monitoring, the claim dies. If signals are detected and verified, the conversation shifts dramatically. Radio astronomy is also a tool for debunking. Many claimed anomalies, from fast radio bursts initially thought to be alien signals to mysterious pulses that turned out to be microwave ovens in the observatory cafeteria, have been explained by natural or human-made sources. The field has a strong culture of skepticism and verification. Whether 3i Atlas is natural or engineered, radio astronomy is a frontier tool for discovery, and for now, the silence from the object speaks louder than any alleged pings. Next, we wrap up the investigation, reviewing what we've learned and looking ahead to what comes next in late 2025 and early 2026. Part 15, Wrap Up and What's Next in late 2025, early 2026. Let's bring it all together. We started with a claim, a dramatic one, that 3i Atlas might be lining up with Earth. The claim was based on real data, a reported non-gravitational acceleration of 0.02 millimeters per second squared, and a simple calculation showing that 50 days of such acceleration could produce a velocity change of 86 meters per second. The arithmetic is correct. The data are real. But the extrapolation, the leap from there's an acceleration to it's targeting Earth, relies on assumptions we can't verify. The acceleration would need to persist, to be pointed in the right direction, and to align with Earth's orbital position at exactly the right time. None of that is established. We examined the trajectory and missed distance. Official sources say 3i Atlas will pass Earth at approximately 1.8 astronomical units, about 270 million kilometers, on December 19th, 2025. That's far. Very far. Converting that into an intercept would require a much larger velocity change, applied over a longer period, with precise timing. The numbers don't support the Earth lineup claim. We explored the natural explanations for the acceleration. Outgassing, the sublimation of ices creating thrust, is the default hypothesis. But the required mass loss rate is high, at least 1/6 of the object's mass over a month, if Avi Loeb's calculation holds. That should produce a massive coma, something telescopes haven't definitively observed yet. The jury is still out. We also entertain the exotic hypothesis. Could 3i Atlas be artificial, a probe from another civilization? The acceleration, the size, the trajectory all raise questions. But there's no smoking gun, no radio signals, no non-volatile thrust signatures, no definitive proof. The hypothesis remains speculative, intriguing but unproven. The social media narrative amplified the claim, turning a scientific anomaly into a story of alien interception. That narrative spread faster than the science, blurring the line between data and interpretation. It's a reminder of how information flows in the modern age, how uncertainty becomes spectacle, how pattern-seeking minds fill gaps with drama. We looked at what happens if the worst-case scenario were true, if the object somehow did intercept Earth. The consequences would be catastrophic, an extinction-level event. But the chain of assumptions required is long and fragile. The object would need capabilities, intentionality, and timing that border on implausible. We also widened the lens connecting 3i Atlas to broader trends in space science. Exoplanet atmosphere imaging, dark matter research, AI-driven orbit prediction, radio astronomy, all feed into the context. This isn't just about one object, it's about how we study the universe, how we detect anomalies, how we interpret data, and how we prepare for the unexpected. So what are the key takeaways? First, 3I Atlas is a rare, interstellar visitor, scientifically valuable regardless of whether it's natural or artificial. Second, the arithmetic behind the 86 meters per second velocity change is correct, but it doesn't automatically imply Earth impact. Third, key unknowns remain: the vector of the acceleration, whether it persists, the timing relative to Earth's orbit. Fourth, observations coming up in late 2025 are critical: mass loss, astrometric residuals, spectroscopy, radio monitoring, all will clarify what this object is. Fifth, while worst-case scenarios are dramatic, they hinge on many unverified assumptions, and official agencies say no threat. Sixth, broader science fields converge on 3I Atlas, making it a nexus for multiple lines of inquiry. Let's talk about the timeline. Perihelion occurred around October 30th, 2025. The object has passed its closest point to the Sun and is now heading outbound. November marks the ramp-up of observation campaigns. The object is emerging from the Sun's glare, becoming easier to observe. December 19th, 2025 is the closest Earth approach. This is the key date, the moment the social media claim pointed to. By then, we'll have weeks of additional data. Early 2026 brings the outbound phase, with a possible distant flyby of Jupiter around March. After that, 3I Atlas fades, moving deeper into the outer solar system and eventually back into interstellar space. What should you watch for? Official orbit updates from NASA, ESA, and other space agencies. Look for refined calculations of the missed distance and any changes to the trajectory. Pay attention to spectroscopy results. Are volatiles detected? Is there a coma? Does the colour continue to be unusual? Watch for imaging reports. High-resolution photos from Hubble or JWST might reveal surface features, jets, or other structures. Monitor radio telescope announcements. Any signal detections at 1.4 GHz or elsewhere would be huge news. Also, watch the contrast between media narratives and scientific statements. How do mainstream outlets report the story? Do they emphasize caution or sensationalism? How do scientists respond to the social media claims? This interplay between public perception and scientific rigor is part of the story too. If nothing dramatic appears by early 2026, what then? Does that mean the maneuver claim was wrong? Almost certainly. If the object behaves like a comet, showing predictable outgassing that weakens as it moves away from the Sun, if the acceleration drops or stops, if no radio signals are detected, then the natural explanation wins. 3I Atlas joins the ranks of interesting but ultimately normal interstellar visitors. But if anomalies persist, if the acceleration continues far from the Sun, if mass loss is minimal despite the thrust, if radio signals are detected, then we have a genuine mystery. That's when the exotic hypotheses stop being speculation and start demanding serious investigation. Will 3I Atlas settle into interesting but natural status, or will it become the first confirmed engineered interstellar probe? The answer is coming, not from social media speculation, but from telescopes, from data, from the patient work of scientists who measure, analyze, and interpret. One final thought. The universe doesn't owe us comfort. It doesn't care whether we're ready for its revelations. For centuries we've been gradually learning that we're not special, not central, not alone in any cosmic sense. Every major discovery has been a step toward humility. 3I Atlas, whatever it turns out to be, is another step on that journey. If it's a comet, we've learned more about the diversity of interstellar visitors. If it's something else, we've learned that the galaxy is more interesting and perhaps more crowded than we imagined. Either way, the object reminds us to look up, to stay curious, to question, and to prepare for possibilities we haven't yet imagined. The investigation isn't over, it's just beginning. The next few months will tell us whether the social media claim was a flight of fancy or whether something stranger is unfolding. By early 2026, we'll know. Until then, watch the skies. The universe is watching back.